Okay, off we go. Real quick, 2 announcements. Don't forget, of course, attendance quiz, attendance code, and all that. You got about a minute and a half left. Also, just real quick, I wanted to comment. Several students have been asking me about when are we going to get the exams back. My general goal is always to get them back to you within about a week. So I'm aiming. No, not promising, but aiming to have them returned to y'all on Friday. So we'll see what actually works out. Okay, last time we were talking about the implicit function theory. At least we were starting to get the ball rolling. And again, the question is, if you have an equation given to you, and an equation describes a curve, and of course we can always view an equation as a level set. So very importantly, when we have this capital F defined, we're looking at a level set of capital F. So notice both x and y are input variables into this capital F. The question we want to address is, let me say it sloppily first. Can I view y as a function of x? Well, that's a flat no in this. Failed the vertical line test, perfectly obvious, right? The actual question we're interested in is, can we locally, at a given point, let's say this one, for example, can we locally view y as a function of x? Now, locally, if all we're interested in is just some little neighborhood of some point in the xy plane, then now this is the only part of the curve we're actually interested in. Right? Now, that little piece of curve passes the vertical line test. Flying colors, no problem. Right? So that's what we mean by, can we locally view one variable as a function of the other, or if there's more than others. So that's a big question. Now, why would we care about such a question aside from, mathematicians liking to play games? And the answer is sometimes when you have a curve, and let me go back to considering the whole thing, sometimes you would like to be able to I don't know. Maybe I want to compute what's the slope of the tangent line to this curve, let's say at a point like this. Right? And you'll probably remember from high school calculus that what you do is you do implicit differentiation. Right? And so you effectively treat y as a function of x, and then whatever you have in this equation as you go through and take derivatives, every time you see y, you're like, okay, well that's a function of x, and you proceed, and then dy dx shows up in your equations, and you solve for it. And that works great, except for one thing. If you're going to just treat y as if it is locally a function of x for the purposes of taking various derivatives, how do you know it actually is a function? Right? So that's the cart before the horse kind of a thing. You have to establish that you're looking at a point where y actually is, at least locally, so that you can talk about tangent lines and stuff. You need to establish that it's at least locally a function of x before you start going around taking derivatives of it. Right? So very importantly, you can only take derivatives of functions. Right? Look back to your definition of a derivative in a single variable calculus textbook. They talk about the derivative of a function specifically. Right? You cannot take a derivative of a bicycle, is my silly little metaphor there. So you've got to establish that's the case. And by the way, don't take it for granted because, sometimes the answer is no. And you look at a point like this one here. Nope. You lose. You can't do it. It doesn't matter how local you restrict your attention, no matter how little of the curve in the vicinity of that point you pick, it's always going to fail the vertical line test because it's always, it's at that point in the process of wrapping under itself. And you just can't do it. So it's not that dy dx is infinity. Oh, no, definitely not. And it's not that dy dx would be a reasonable question to ask, and the answer is that it's undefined. That's not it either. It's that I don't even know what you mean by dy dx. It's not that we computed it and it blew up in our face. It's that there is no derivative because it's not, even locally, a function. Does that make sense to everybody? Everybody see kind of what we're up against? It's a pretty big deal. So that's the concern. How we deal with this. This is the nut, I think. This is the good intuition for how we answer this question. And I'm just going to kind of walk you through it. And again, let's not worry about rigor. That's not what this class is, right? But a problem like that, the problem is that the curve is wrapping under itself. And you're going to fail the vertical line test all day long there because, well, it's wrapped under itself and you're going to have these multiple intersections. Right? So the fact that it's wrapping under itself is the problem. And if you think about it, wrapping under itself is only possible because it's vertical there. It has a vertical tangent line. And keeping in mind, of course, that we are talking about an equation and therefore a level set. And specifically, this function f is a function whose level set describes the equation. Vertical tangent line means horizontal gradient because gradients are always perpendicular to level sets. And then if you sort of, okay, all right, what does that mean? You think about what the gradient is. The gradient's made up of the various partials. What would it mean for that gradient to be horizontal? Well, in this case, it would mean that the y partial of capital F would have to be 0. So just to kind of summarize, then this line of reasoning suggests that a problem would imply that the y partial has to be 0, and we're going to turn this into a useful result by taking the contrapositive. Remember, if P implies Q, not Q implies not P, right? So the contrapositive is, well, if you compute the y partial and it's not 0, there's no way there could possibly be a problem because problems would force this to be 0. This is the useful version of this argument. And it's really a nice little result. You got one little thing to compute is a particular partial derivative. Once you've computed it, here's a very simple test. The answer is either 0 or not 0. And if the answer is not 0, you're good. And then go ahead and do all the implicit differentiating you want. It's all fine. It's cool. Go ahead. It's all fine. Okay. Now, in some abstract sense, this is something that could be done in a high school calculus class. The sticky wicket would be the argument about the gradient here. They don't talk about gradients in high school calculus. Okay, so we would have to finesse our way around that, and there are ways to do that. You could make roughly this argument in a high school calculus class, and ideally it should be done, but I'm aware that it typically isn't. What we're going to do here really wouldn't make any sense in a high school calculus class at all. This is unavoidably multivariable. So, very similar question. If we have an equation involving 3 variables, you can always write that as a level set, which is described by an equation, which will give us a surface, which would look something like that. And again, we can ask reasonable question. At some point, can I view y, or can I view, let's say, z as being a function of x and y? So again, let's consider a couple of cases. If you pick a point, like, let's say this point right here, locally means I'm only going to look in the immediate vicinity of that point, looking at just the part of this surface that's in this yellow sort of neighborhood of that orange point. So ignoring all this stuff down here, it's not our problem, right? That's not local to this point. Looking only at that little bit of surface, does it pass the vertical line test? And yeah, just fine. Right? So the little piece of surface would be something kind of like this, and yeah, passes the vertical line test. No issues. The only issues would come up at points like this. And let's see here. I was going to have this out, and then I forgot. Where the surface does something, let me do it like this, something like so, right? If you're looking at a point, let's say about right there, the surface is, at that point, is immediately in the process of wrapping under itself, and that's the problem, right? So you make the same argument then. The problem is that it's wrong color. Is that it is wrapping under itself. Wrapping under itself would mean that you have a vertical tangent plane. Now I want to emphasize, when I say it has a vertical tangent plane, I don't know how it's vertical. It might be parallel to the y-axis. It might be parallel to the x. I don't know. No, I don't care, right? It can wrap under itself kind of in any direction it likes, but it's the fact of it wrapping under itself. It's the fact of having that verticality to the tangent plane. That's the problem. And then again, since we're looking at level sets, right? Vertical tangent plane means horizontal gradient, and again, you think geometrically, what does that tell me about this gradient vector? And it's made up of partial derivatives, and if it's horizontal, that means the third one is 0. So the z partial is 0. How are we doing? Everybody buying it? Notice how the argument that we make here, now we have to, tweak the picture and everything's a little bit different, but the strategy, the argument that we're making here is morally equivalent to the argument we made here. Okay. All right, so here's a cool observation, really kind of the big observation. Well, let me not get ahead of myself. Notice I didn't yet address the question of, hey, can I view x as a local function of y? We didn't really directly address that, but I bet you could probably come up with an argument kind of analogous to this, right? Where instead of a vertical line test, you'd be imagining some sort of a horizontal line test where you're trying to view x as being a function of y. And then likewise, in the multivariable case, can I view y as being a function of x and z? Right? And so the way you're going to answer that question, you're going to draw kind of analogous pictures, and I think it's a good exercise to do. I encourage you to think through, at least one of these other questions that you could entertain here. Here's the pattern that you're going to notice. In every version of this question you ask, whichever variable you want to view locally as being a function, that's the one, the partial with respect to which answers the question. So if you want to know y is locally a function, it's the y partial that's going to answer that question. Here we entertained viewing z possibly locally as a function, and check it out, z is what you're taking the partial with respect to. That pattern holds. So that's the theorem, and I'm going to go ahead and write that down as a theorem now. Here it is. Now there's regularity issues. This function that we're talking about, it does have to be C1. And by the way, I just this morning noticed that should be a capital F. I'm sorry, I don't know why I wrote it as a little f. Nobody's ever corrected me on that. Anyway, I'm sure people knew what I meant and just didn't write it down. But this should be capital F. Sorry about that. So we need that function to be C1. The function whose level set describes our surface or whatever it is has to be C1. And with that said, notice the punchline. Whatever variable you want to view locally as being a function, that's the variable, the partial with respect to which needs to be non-zero. Everybody buy it? That's what this is right here. If you want to know a variable can be thought of as a function, take the partial with respect to that variable. Okay, let's do one. Okay, now I did something convenient here. I got an equation describing a surface, and the convenient thing that I did, I set it up where it's already a level set. So just a heads up, life doesn't work like that, right? You know, we can't expect any way that it will. So if you have some equation where you've got stuff equals other stuff, just move everything over to one side of the equation. Make sure that it's been written as a level set, because, reminder, coming back over to the argument, it is critical that the surface be a level set, because we make the argument that gradients are perpendicular, and gradients are only perpendicular to level sets. Is that cool, everybody? That's a really big point. You got to make sure that you do that. So make sure you rewrite your equation as being a level set of a function, and having done so, that's the function that is your capital F in this case. All right, so that said, we've got this great big function of x, y, and z, and notice the usual question. The usual question is we want to know, hey, one of those, can I view one of those locally as being a function of the other two? Right, so can I view x as being locally a function of y and z? Well, I'm going to follow the usual pattern. Whatever our capital F is, that's what we're taking a partial of. And whatever variable we want to view as being a function of the others, that's what we take the partial with respect to. Everybody happy with that? Okay. Just following this theorem right here. And then it's all over but the shouting. We do have to actually take the partial. Don't forget the question here says we're looking near a particular point. We're looking near this point 1, 2, 3, so we have to evaluate at the point 1, 2, 3. That's the point we're actually trying to decide. It's going to be different for different points, right? Because the surface is doing different things at different points. And notice the answer. That partial at that point is non-zero, and non-zero means no problem. So yes, x is local to that point anyway, a function of y and z. What do you think? Is that cool? All right. Okay, so knowing that it's a function, then now we can start asking about its derivative. Now that x is a function and not a, more to the point, it's a function, full stop. I can ask, what is the partial of x with respect to y? What is the partial of x with respect to z? Right? X is a function of these variables. We can talk about its partials with respect to these variables. And how do you compute those partials? Next question. So there's two approaches to take here. This is what I'm going to call a better, mathematically better approach, and it's clunky and bulky and frankly kind of unnecessary for practical sort of, rubber meets the road purposes. So I'm not planning to talk about this. If you're curious, if you want to see the full-on version, come on and talk to me in office hours. I'll be very happy. It's actually pretty cool. I mean, I think this is a neat argument. I'll be very happy to talk you through it, but you don't have to. I'm just going to take you down here to what I'm going to call the good enough and much more convenient take, which is this right here. And let me walk you through this this setup. We've got this function f. It's a function of, let's say, x1 through xn, right, various variables. By the way, we're looking at a level set of f, which means we're setting f equal to some constant. So I'm going to say it's equal to c. Typically 0, but it doesn't have to be. Any constant's fine. And just to be clear, I'm going to highlight that in gray. I like gray for constants. And then let's see here. We've talked about how to decide if one of the variables can thus be viewed as a function of the others. Here I'm viewing xi as being a function of the others. right? Because as soon as you say f equals a constant, that describes your surface or your curve, and then it's on that surface or curve that you can view xi as being a function of the others. And so if xi is a function of the others, I can ask, okay, what's its partial with respect to xj? Let's say one of those others. And keep in mind what partial means. Partial means that all the other variables get held constant. Okay, so those are constants. This is whatever's in there is constants. All this down here, all constants. So this is our scenario. Once we set f equal to a constant, once I decide that I can view xi as being a function of all these others, but specifically xj, reasonable question, when you change xj, how much does that change xi? Now, here's how you answer that question. The way you answer that question is by writing down the chain rule. Now, you should have all sorts of red flags going off in your mind right now. Hey, you can't. No, that diagram, that doesn't follow the rules. This is not evidently a composition where the outputs from the first function are the same as the inputs to the second function. This just isn't, right? It does not do that. So, bad, right? Problem. And you can fix that by introducing new variables, and that gets you to this. And again, if you want me to walk you through, I'm happy to. Feel free, no problem. I think it makes the punchline, I'll say it like this, the punchline is that if you just take a certain point of view here, and if you're willing to believe me that this is fine, it's going to be okay. This particular little math crime will not lead to wrong answers. Right? If you're willing to buy that, then we argue as follows. I'm going to look at the overall chain rule derivative of f with respect to xj. Now, so there's a composition. Again, it doesn't look like a composition, but anyway, we're going to make changes to xj and then see how those changes propagate to cause changes in f. We're going to do that calculation and go from there. So here's the first observation I'm going to want to make. How much does f change? Well, we know how much f changes. It doesn't. The whole point to all of this, right? The way that I can view xi as being a function in the first place is by saying, look, I've got to stay on this level set. That's what we mean when we say f is a constant. We're stuck on that level set, and if it's not changing, then its rate of change is 0. That's the first observation. The next observation is, well, yeah, but there's going to be changes that propagate along that path, and that path gives this term. And there's also going to be changes that propagate, well, just sort of directly on that path, and that gives this term. So wait a minute, f can't change. The overall derivative has to be 0, but the overall derivative is also the sum of these two terms. So the sum of these two terms has to be 0. Is that cool? Everybody's on board? Okay, and then it's all over the shouting at this point because the thing that we're interested in the partial of xi with respect to xj, and it's right there, and you can totally just solve for it, and here's the formula. That's what you get. So this is a handy-dandy little formula to make sure that you know for how to compute an implicit derivative for multivariable functions. And I'm going to do an example in just a second. All right, now before we go on, there is a eyebrow raiser on the page. Some of y'all may be wondering already, but the question is, hey, wait a minute. Can't I, I didn't want that color, sorry. Can't I sort of cancel these? And wait a minute, isn't the denominator of my denominator, isn't that my numerator? Kind of like so. And wait a second, isn't the denominator of the numerator the denominator? Kind of like so. And hey, wait a minute, doesn't this work without the minus sign. Right? Everybody see the temptation there? Very, very tempting. Very tempting to think, the minus sign, I don't know, I must have made a mistake somewhere in the previous calculation because this seems like it ought to work. And you might already be seeing what's wrong with this argument. What's wrong with this argument is that these are not the same things. Right? Again, you can't cancel these. Partial derivatives are written as fractions, and in a narrow, situationally dependent sense, they kind of are fractions. But in the sense that I'm doing here, like partial f is a meaningful thing by itself, independent of the context, absolutely not. This is garbage nonsense reasoning. Right? And we've seen this in the past. We've seen when we first wrote down the chain rule, we saw, you cannot just go around canceling these partial differentials like that works. It just does not work. So that's what's wrong with this reasoning, but it still remains kind of, but where's the satisfaction, right? I mean, why should I feel good about that minus sign? And here's my best take on that. Let's see, and by the way, I want to get the colors. So that's the green, and this is the blue. The satisfaction, for me, first of all, I'll point out this minus sign is ultimately a consequence of this being a plus sign. The way you solve, right? The fact that this is a plus is what makes this a minus. So why is this a plus? And the reason it's a plus is because, again with the wrong colors, the contribution along that path and the contribution along this path are supposed to cancel. These are supposed to be opposites of each other, and therefore they add up to 0. They're supposed to be opposites of each other because f can't change. The whole point is that these have to cancel because f can't change. However much the dark blue one suggests f would be changing, the purple one has to contribute exactly the negative so that f will not change. So these two things should be negatives of each other, therefore that should be a plus, and therefore this should be a minus. Anyway, that's my take on it. I hope that gives you some satisfaction. The relevant, sort of immediate relevant upshot to you guys when it comes to taking an exam is make sure not to forget this minus sign, just from a test-taking standpoint. That minus sign is a really big deal. That one little minus sign, let me just remind you, there's different kinds of sign errors. Right, so there's the sign error of the sort, I had 7 minus signs and I counted wrong. I counted 6, and so whoopsie, we made a sign error, right? And that happens to the best of us. It's trivial. It's a consequence of not counting correctly. I know that y'all can count, and if you miscount, I do not judge you mathematically for it, right? I know that's just a little whoopsie doodle that happens to anybody. That's not what this is. Right, so very importantly, this minus sign is the distinction between a perfectly valid formula, as I have it written here, versus if you take that sign error, if you take that minus sign away, what you have here is now, the idea that this is equal to that divided by that is just nonsense. And not only is it nonsense, it makes it look like whoever wrote that down might actually think that these cancel, which they really, really don't. I mean, it's fundamentally misguided, right? So that one little minus sign, right, turns garbage into valid. So be really, really careful about that. I mean, on an exam, this minus sign will amount to a lot of points. And this is, again, double-edged sword. You can think of that as, I'm going to lose a lot of points. Or you can, and I would encourage you to think of it as free points all you got to do is remember the minus sign, right? And that's going to count as points. So I encourage you to take this glass is half full approach to this point. Does that make sense to everybody? All right. Okay, so let's do one. I'm going to take this, where am I? Here we go. I'm going to take this example. We've already looked at this surface, viewed it as a level set. We've addressed the question of whether x is a function of y and z. In the affirmative, yes it is, at least near that point. And now we're going to ask, okay, fine, since x is locally a function, what's its partial derivative hang on. And my pen decides that that's a good time to quit. Okay. X is a function. We've established that. So what is the partial derivative with respect to z? It's a function of y and z. Let's take the partial with respect to z. All right, is that cool? Everybody see where we're going? Okay, well, now here's the problem. We've got an annoying little problem here. The formula we just derived was in the context of where f was a function of variables named x1 through xn, and now we're trying to apply this formula where there's no x1 through xn. The variables are called x, y, and z. And so, okay, well, it's irritating. So, okay, do I have to draw a whole new diagram, or do I need to do some sort of copy-paste situation where, okay, well, I feel like x is playing the role of xi and z is playing the role of xj. That can be confusing too, right? So here's what I do, and this works great. When you're going to do an implicit differentiation, the very first thing that I do, I put that minus sign down there. I'm not taking any chances that I will forget that minus sign and that people will think I don't know what I'm doing, right? So minus sign first, right? Everybody good with that? If only strategically, write that minus sign first. And then, as much as I just trashed this idea of the cancellation is mathematically nonsense, but it's a nice little memory tool, right? And I 100% use this nonsensical idea that, oh, well, yeah, it's like these were going to cancel. And then, oh, wait a minute, let me get my colors straight here. The thing that I want to be my numerator, well, that's going to be the denominator of my denominator, so I'll put that there. And the thing that I want to be take the partial with respect to, that's my kind of denominator. That's going to be the denominator of the numerator. And I put that right there. And having remembered that minus sign from the very beginning, now I have the right formula. Right? So it may be nonsense, but it is a convenient little memory trick. So that's what I would encourage for y'all to do. Let me pause before we wrap this up. Everybody's on board? All right. So it's mostly all over with the shouting. You take various the indicated partials, and that's plug and chug. You plug in the point that we're interested in, and that turns it into a number, and boom, there you go. Just arithmetic. Okay, so one last thing, and this is another warning. Watch out for the following landmine. I have already talked about the landmine that is this minus sign. Right? Don't forget that. It's a big one. The other one is, don't forget to check that the thing you've been asked to take a derivative of is actually a function. Now, I built that into this first example. In this first example, the stated purpose of the first half of the example is to determine if x is locally a function. And then I explicitly doffed the cap that has already been established when I did the second half of this example, right? It will not always come to you in this form. In fact, it will rarely come to you in this form. Usually, questions of this sort will come to you like this. It'll come to you as, and by the way, when I say, usually, I don't mean on exams, although also on exams, but I just mean in life. When you're doing engineering stuff and you find yourself looking at an equation and wanting to know one of the related partials, it's going to be, well, here's the equation, this is the partial I want to know. And it's nowhere in the statement of the question going to actually say, by the way, don't forget, don't go around taking derivatives of bicycles, right? You got to establish that this thing is actually a function. It's not going to say that. So it's your job to remember that you've got to check that. So when you see a question like this, you've got to first ask, wait a minute, whoa, hey, how do I know that x is actually a function? You want me to take a derivative of something? It doesn't look like a function to me. Where does it say x equals? How do I know that's a function? And you got to come up here and do this business. Take the appropriate partial, plug in the appropriate point, establish that it's not 0, establish that means yes, it is locally a function. And then and only then can you move on to actually taking the partial with respect to z, like so. And just an FYI, and I've got it written down here, what I wrote here was that checking if it is a function is an important part of the solution. Just a FYI, it's typically about half of the points on a question like that. Right, so if there's a 10-point question that looks like this, half of the 10 points are going to be for establishing that x actually is a function of y and z, at least locally. And then the other half of the points will be for this calculation. Does that make sense to everybody? Okay, so make sure that you actually do that on such questions. Okay, moving along. So we're done with Chapter 2. Moving on to Chapter 3. We've already done 3.1. You may recall I did 3.1 early, because I like to use 3.1 in 2.5. Okay, so there's kind of two parts to 3.2. There's this part, establishing certain useful objects that we're going to use a lot of, especially when we get Chapter 6 and 7. We're going to use this tremendously. Very important setup. And then there's all this business about computing arc lengths and arc length parameterizations, and frankly, it's a little bit of a digression, and it's cool math, and it's important to math in various ways, but it's not part of where we're heading to. It's not going to help us get to chapters 6 and 7. And so I'm going to go pretty quickly through the rest of 3.2. It's going to effectively be kind of a plug and chug kind of a thing. So anyway, let's go through this important part first. Some of this we already know. Y'all are already aware of the idea of a parametric curve. And of course, a parametric curve would be something like this. And y'all are already aware, I presume, that we can, we've talked about derivatives, right? R prime is V. And now I'm going to make what I'm going to call a modest proposal that I can write dr is r prime dt, and let's just think about what this would mean if I write dr equals r prime dt. What is this dr? Well, r prime says change in the output per unit change in the input, so dr is the change in the output. Dr, and by the way, in general, that's what a differential is. D means a linear estimate of how much something changes. Right? Linear estimate, to be fair. R, of course, is position. So this is just saying, okay, what's our linear estimate of how much our position has changed? And the linear estimate would be something kind of along these lines here, like this. I would have gotten purple there. Right, now the actual change in position, I start here. I'm not going to end there. I'm actually going to end here, because the curve doesn't always behave exactly as it did at this point where I took the derivative and from which I extrapolated. Right? So, yeah, sure, reality is going to be a little different. This, though, is our linear estimate. Is that cool? Okay. All right, let's see here. Now, the next thing I want to point out, another reasonable object of interest, ds. Remember, we use s to represent distance, typically. So ds means what is our linear estimate of distance? What is our linear estimate of the length of this little piece of curve? And let's see here. Let me focus on now this little piece, this in green here, this little piece of our parametric curve. It has a length. ds is our linear estimate of that length. And I think a pretty reasonable case could be made, whoops, wrong color, that ds is the magnitude of dr. And if you think about it, dr tells me both what direction I'm estimated that I have moved, and how far I've moved in that direction, and how far I've moved is the same as the length of the path along which I've moved. So magnitude of dr, I think that's a reasonable take, that the length is the magnitude of dr. Okay, if you're willing to buy that. How are we doing? Is everybody with me? Feel free to shoot a hand up if you have a question. Okay. All right. So the last thing I want to introduce. Oh, whoops. And I tell you what. Let's see if my good stylus is back in business. Nope. No, I'm on the eraser. And yep, back in business. Okay, hang on. Put this in here. Okay. Last thing I want to talk about is this thing called the unit tangent vector. And by the way, I just want to point out there's actually 3 tangent vectors that we're going to be interested in here. 3 tangent vectors. One of them is the velocity, namely r prime. And the velocity is going to be some, vector like that, non-unit vector. Then, of course, there's the dr vector down here, our position differential. That's a tangent vector. But now we have this unit tangent vector. It's our sort of third tangent vector. And by the way, it's the unit vector pointing in the direction of v, and we already have a formula for how to compute a unit vector in the direction of, well, whatever you're interested in. So easy formula for how to compute the unit tangent vector. And while we're here, I want to justify why it is that TDS is dr. And it's just, you can view this as a calculation. I mean, if you want to take an equations point of view on this, you could take your t. There's your formula for t. You could take your ds. Here's your formula for ds. And notice if you just multiply green times orange, let's see, you get v dt. Yep, you get dr. Right? So just from an equations point of view, it works. But here's I think a better way to think about it. Let's just talk about what are the defining characteristics of dr and what are the defining characteristics of TDS. Well, dr points tangent to the curve. So does t. And so does, therefore, TDS. So these two vectors point in the same direction. That much is clear. And now let's ask, what's their magnitudes? Well, the magnitude of dr is ds. The magnitude of TDS, also ds. So what we have, if you just look at the, by what's the direction and what's the magnitude, both of these things have the same direction, they have the same magnitude, so they're the same vector. And I like that point of view. I think that's more sort of intuitively satisfying. The equations are always good for sort of peace of mind, but I like the satisfaction of the intuition. Okay, That's the most important part of 3.2. Now, that said, if you do, for whatever reason, want to compute the length, the overall length of a parametrized curve, well, we know how to compute ds. I know how to compute the length of any little piece of curve. Any little piece of curve. Magnitude of v dt. You want to add that up over the entire curve? Sure, cool, integrate. All good. Right, nothing to it really. So this is the formula for computing arc length. It's very plug and chug. You'll notice in this example, we take our given parametrized curve, we take a derivative. There's the derivative. Then we take the magnitude, we integrate, just like in the formula. And then algebra ensues. And by the way, this integral ends up being pretty undesirable. And I'm sorry to report this is pretty often the case. These integrals get ugly pretty routinely because they're integrals of magnitude. Magnitudes are square roots, and square roots make ugly integrals. Okay. All right. Okay, let's see. The last thing we'll probably have time for is this idea of arc length parameterization. Let's start with the idea of a reparameterization. Y'all have seen curves like this. We've talked about the graph parameterization. It's an easy way to create formulas for x and y that work in the equation. Now let me observe, and this is going to seem weird and pointless, but yeah, okay, but still this wacky curve also works. Right, so here are two different parameterizations of the same curve, and of course there's infinitely many parameterizations, and parameterizations are not unique. So how did I get this parameterization? You might notice that basically everywhere I saw a t, I put q cubed plus q. And the upshot here is that whenever you have a relationship like this between your existing parameter and a new parameter, plug it in. New parameterization, right? So algebraically, it's pretty straightforward. If you plug in for your old parameter, you get a new parameterization in terms of a new parameter. So, no big. The trick, the clever move, is when you do that with arc length. So if you have a parametric curve parameterized by time, notice with some base point set, let's say where t equals 0, at any given time t, I can compute, let's see here, colors. I can compute this distance, s, that's the arc length, and that gives me a formula for s as a function of t. And so again, just like in this case, I've got an algebraic relationship, plug it in. That's all it is. Right? Now, to be fair, all right, here I will have s as a function of t. I'm going to need t as a function of s to plug it in. So you do have to invert that function. That's a little annoying, right? It's a bother, but that's just algebra. Okay. Now, why would we care about such a thing? It's mathematically nice in some neat ways. My favorite of these points is this one right here. It's intrinsic to the curve. If you take a road trip, let's say we drive from here to Raleigh, get on 40, off we go, right? Well, I can talk about parameterizing with respect to time by, when I start, I'll note what time it is, and then as I drive along, okay, let's see, 5 minutes into the ride, I'll make a note of where I am, and you can just keep track of position as a function of time. Anytime you drive in the car, you can think of position as being a function of time. But let me point out, you can also think of position as a function of distance. And it's the highway department has done this for us. It's called mileage markers. right? They're literally telling you location as a function of distance. When you see mile marker 270, right? That's where that's the location. That's location is a function of distance. At where that marker is the location, and it's telling you in terms of distance traveled from some preset location. So mileage markers are a arc length parameterization of the highway. Your personal road trip that you take on that highway is a time parameterization of the highway. So that's the difference. The example, I think, is a pretty straight read. Take a look. The algebra gets ugly. We can't solve for t here. These problems do tend to be algebraically inconvenient. But structurally, this is a pretty straight read. Okay, see y'all later. Have a good rest of your day.